Let's take a closer look at our graph of metabolic rate as a function of environmental temperature. To review, this purple graph represents a temperature regulating animal. The green line represents a temperature conforming animal. You'll notice that the minimal metabolic rate of the regulating animal is about 10 times this minimal metabolic rate of the conforming animal. This is a general relationship that holds that it costs about 10 times more to be a temperature regulating animal. But what is gained in that more expensive lifestyle is an ability to do more work. So it is also true that an endotherm is able to sustain about 10 times the metabolic rate that it has as a basal metabolic rate. So this animal would have a maximal sustainable metabolic rate of approximately 400 units, which means it could use and replace 400 units worth of ATP so long as it had food to do so. The relationship between these two values is called aerobic scope. Relationship between basal metabolic rate and maximal metabolic rate, and as a rule of thumb, it's a 10x relationship, just as the difference between regulators and conformers is, as a rule of thumb, a 10x relationship. Okay, this animal seems to be within its thermoneutral range at between 60 and 70 degrees and has a basal metabolic rate of 40, the amount of fuel it has to spend when it's not spending any energy staying warm or staying cool. It seems to have a cost of staying warm or cool of, let's say here is 60, so 60 down to 40 is 20, and that's over 20 degrees. So for every degree below the thermoneutral range, there seems to be the cost of a metabolic rate unit to compensate for that decreased temperature to maintain the body temperature. Now, amazingly, the maintenance of body temperature is a function of how much it costs, how fast heat is lost, how much it costs to replace that heat. And you can use that relationship and extrapolate down to discover what the body temperature set point of this animal is. So this animal, because it spends a metabolic rate unit per degree to get to its temperature set points at temperatures below its thermoneutral range, and where its thermoneutral range begins and its basal metabolic rate, that's enough information to discover from this graph what the body temperature set point is. This is the basis of, CSI shows where they take a thermometer and stick it in the guy's liver and find out how long he's been dead, because we lose heat at a predictable rate, just as it is shown here that we are losing heat at a predictable rate and replacing that heat with metabolic energy costing mechanisms. Okay, what else can we learn from this curve? Well, I'm not wearing a coat as I make this video. But if I were to make a video wearing a coat, I argue that I would probably be comfortable in a lower set of temperatures. And I argue that it would cost me less energy to stay warm when I was below my thermoneutral range. So let's make up a new situation like that. Basal metabolic rate stays at 40. Now, do you think when you put a coat on, you change from 37 degrees? Do you think that when this animal puts a coat on, it's going to have a temperature different than 100 degrees? I don't think so. That would contradict the fact that this is a regulator. Remember, if this is environmental temperature over here, and this is body temperature here, remember, this is the relationship. That's a horizontal line in case you're blind and can't tell. That's the relationship we expect. Body temperature is not going to change with environmental temperature. Body temperature is not going to change when we put a coat on. We are protecting this body temperature. Our physiology will change to maintain this body temperature. So, what does that mean? Well, this is all, I think, rather intuitive. It's going to cost less to stay warm, and we're going to be comfortable at cooler temperatures. So this is a version of cold adaptation. I raise sheep, so I use sheep as an example a lot. Sheep in the winter have a much denser, much more voluminous coat. That's all wool. And so they are comfortable at lower temperatures, and it costs them less to stay warm at any given temperature. So below their thermoneutral range, it takes a lot less energy to stay warm. And to what extent that is, I can sort of figure out by saying, they're still going to be 100 degrees. This is going to be their new lower critical temperature at this same, this new thermoneutral range, but same basal metabolic rate. I can extrapolate back to find out what their new cost of staying warm is going to be. And so, oh man, I'm off the graph. That's going to be a hard thing to go down and over. But that's okay, because I know what the relationship is. I know I've gone from 100 to 40. So I know something over 60 is going to be my new rate. And let's see, how much have I gone down? From 40 to 0. So that's 40. So the new cost of staying warm here is going to be 2/3 of an MRU per degree. Okay. What you don't know too much about, what no one knows too much about, is how in a cold adapted animal this cost of staying cool line will change. It's just not predictable. I will never ask you to describe a change in this line unless I give you the specific numbers telling you how it's changed, because we can't predict how it will change. What we've seen here is an animal before and after cold adaptation. Thermoneutral range changes, but the basal metabolic rate doesn't. The cost of staying warm does. And cold and warm adaptation really are quite analogous to taking off clothing or putting on clothing. That's the predominant mechanism at work in these sorts of adaptation.